I would like to tell our listeners that we have a very interesting ongoing project between different countries and with many participants, biologists, medical researchers, and also mathematicians about some neurobiological questions, in particular with Anne Better, who is present here. We work together on a big project related to rehabilitation of patients after stroke. In particular, patients after stroke can have what is called aphasia. Aphasia, it's problems of speaking for people, for some people after stroke, and of course it's very important problem how to help them to recover their normal language. So there are many things extremely interesting about that, and I hope that from time to time we will organize seminars devoted to this topic, and we will tell you about what is going on. And today it is a pleasure for me to introduce Bенджамин Амбросио, who participates in all these projects and also has many different activities related to neurobiological modeling, because there are very interesting problems, mathematical problems, nonlinear dynamics, complex oscillations, all these questions. And Bенджамин is specialist in this area. So today Bенджамин will tell us about reduced models to generate brain rhythms. Please, Bенджамин, we are listening to you.
Thank you, Vitaly. Thank you for this kind introduction. So, yes, so today the topic of today is reduced models to generate brain rhythms. It's a very specific work. Of course, applications are much more huge, and even our work goes beyond that. So to speak, the outline of the talk, I will start with an introduction just to appeal to the problem. Of course, so we have Anne and maybe other specialists of neuroscience. So you can comment and please give your comments if you want to say something. It's to introduce the problem, but that's a big problem. Then I will speak. We will speak about the very simple math problem, which is an ODE with a limit cycle, and we add noise. What's the relevance of that with respect to the neuroscience question? Then I will introduce a little bit more involved ODE, and again we will put some stochastics in there. I will confront this model with real measurements, and then if the time allows, I will just so I will not give proofs today, even if it's part of our daily work, but not today. But I will just present some math that are some math questions that have been done with respect to that. So let's go with the introduction. So the big thing, right? Rhythms. It's quite a big question. So it's trivial to say, but so since we started to make measurements of the brain with electrical activity, just to say a few examples, theta waves, so waves that oscillate between 0.5 and 4 hertz generally, are associated, for example, with deep non-rapid eye movement sleep. So I say theta is delta, huh? Then theta waves, it's the frequency is a little bit higher, are related to drowsy, not so deeply sleeping states, and so on, so forth. And you have, for example, gamma rhythms, which range of frequency is written here, 1390. It's implicated in information transfer and cognitive process. So I will come back to that, especially gamma rhythms later in the talk. And so this is the first thing. This is a big thing for. So it's a big improvement for the last century, is that we are able to associate rhythms and frequencies that are measured in the brain with external behavior, even mental states. So the sleep, for example, it's they have a very specific decomposition of sleep into this theta, delta, theta, alpha, etc. So it's quite a big thing. So it's quite a big thing to understand what's going on in the brain since we can characterize these states. Another big question that I found to be, and that's a big question in neuroscience, among others, that's we observe that these rhythms synchronize. So at different place for a given stimuli or state, you observe some parts of the brain that have the same frequency. So some people hypothesize that that's something behind there for sure, but what's the way of communication between these parts of the brain. And so there's very active research on these questions from the neuroscience point of view. Yeah, so this slide is just to emphasize again what I've just said, is that really that's a big question, right? Rhythms are the big question. And the point is that, so this comes with tools for measure these rhythms. I will here emphasize 3 of them. There are others. For example, the ECOG that I should put there, but I didn't want to put too much thing. But so the EEG is a quite old instrument now. So it's you have to make the diagonal. It's the C on the left hand side of the slide. So you put some electrodes in the scalp, and you measure these electrical signals at this amplitude, right? So it's a 50 microvolts. And most of for the sleep, yeah, most of the theory right now, the most well known for the public theory comes with EEG. But now that other things are coming, but still EEG is very used in research, and there's a lot of projects going on with scientific projects with EEG. So at the lower level, you have these recordings, local field potentials that are done with macro electrodes, and this is the order of magnitude that you observe in the voltage. So you measure the electrical activity in a local zone of neurons. And then now you can also make recordings at the neuronal level, so a very, very tiny zone with microelectrodes. So you measure the electrolytical activity at the neuron amplitude. So this is known. This is the amplitude of related with the action potential of an individual neurons. Okay, so I want to put some context there. The point is, I will come back to that later, but a little bit more context just for culture and for history. So this is the first human EEG recorded in 1924. So there were some Russian guys. I didn't put them there. I hesitated because this is this takes place in Moscow, but I put the first human. So before there are some Russian guys involved with animals, but Berger, so is from Germany, first recorded and make it public this EEG in 1924. And as you can see, you put some periodic function. It doesn't like cosine, but almost it's a periodic function, and the frequency is 10 hertz. And so clearly you see that this EEG here as a rhythm, as a beat of yeah, you can say that with the eye, it's 10 hertz. It's quite amazing. Again, so this is the implementation of an EEG. You have to amplify the signal to be able to measure it. This is kind of modern recording outputs of an EEG, and you can see that the outputs you can identify. You can extract delta rhythm, theta rhythm, beta rhythm, alpha rhythm in one single EEG recording. The big points for us, I wanted to say that so now that we can measure, you have functions, and there's a room for mathematicians. So and I think that's my personal opinion, but there's no option. Mathematicians can play a role in analyzing the things that are going on in the brain, because we can measure that. And so as a fact, when you start to read some literature of neuroscience guys, neuroscience people, they make a huge use of tools based on Fourier or, for example, wavelets. These are mathematical tools. So I think as part of the mathematical community, we have to get in there, because that's fundamental questions, and yeah, I think we can help in this respect. So now to get to the core of the talk, to make the transition, I will cite this paper. These are from NYU guys. I think it's funny. It's not to advertise, but that's what I come to that. So let me say that. So Lei Sung, as I said, is a mathematician, very well-known mathematician. She was invited to the you know, the Congress of Mathematics. She's not well known, and she's a woman, so yeah, she's quite famous in math. And 10 years ago, she started to study neuroscience, and she told me that she went to NYU classes to take neuroscience with students and to learn. And now she made a couple of papers on neuroscience, Journal of Neuroscience paper, for example, or others. And so she teamed up with Shapley, who works with a neuroscience researcher. And Logan was a PhD student and then a postdoc student of Lei Sung, and he did his PhD, his postdoc between both of them, and is very good at programmation. So he knows about math, he knows how to program it, and they made up a good team. And what I think it's a big thing that they did. It's an interesting thing. They built quite complex network model about V1. And so, for example, they were able to reproduce this orientation selectivity that occurs in V1 when you present some different kind of shapes or oriented shapes. And yeah, their model it's a numerical stuff, but it's quite interesting. And to make the transition to the work that I'm presenting now, I will rely on one of their paper, which is about rhythm. So it's rhythm, but it's on the network. Then my talk, our contribution will be on the lower dimensional model. Okay, so these references have been taken from this paper. I went through one of them, but I follow the narrative here of their paper. So first, the gamma band is observed in a lot of activities. So it's attracting a lot of interest in neuroscience. So these are examples of papers. Yeah, so one of the tools that is very often used to that is the local field potential. And for example, so these guys, I heard this guy. It was a very good talk from this guy Pesaran. I think it's I've seen him one time. It's a very interesting guy. So they are neuroscience guys. There's no mathematicians here, and so using these tools, yeah, in background, the signal in V1 is known to have a 1/f power spectral density. Okay, this the GIA paper. I will come back to that later at the end of the talk. But when you activate the cortex by a precise signal, you start to see a bump in gamma at between 30 and 80 hertz. That's a fact. Now that's observed. Okay, and now what's of interest here is that this rhythm is not always. It's like we saw it also in the EEG. It appears, but then it disappears. We call it bursts. It's very well known in mathematical neuroscience because you do have quiescent periods. You can play with the power, means with the intensity for each frequency, the sharpness. For example, in V1, I'm not going to talk too much about that, but yeah, with the different inputs, the type of the gamma change. So, for example, so the orientation, I'm not going to talk about that, but it has been very well studied. The contrast, the size of visual stimuli, etc. Okay, and so what I'm going to focus is we're doing some math. We're trying to do some math at the simple with simple models. So the main thing is that it's oscillatory, but it's not periodic in the mathematical sense. These rhythms do have some irregularity. Often you observe broadband gamma spectrum. Means that the basis of the function is large, and it wanders, so it goes back and forth. It degenerates, then it comes back, and you have the bits like in music, but they are not the same in magnitude. Also, they degrade and they come back. And so the discussion, it's like this paper is like a discussion about the mathematical characteristics of the observed rhythm and how to generate it. And this is a paper that is going to appear in Frontiers, and it's a very joint work with Lei Song-Yung. So let's start. Let's start with we're doing some math. We start with a very simple thing. Let's start with this very simple model. There's this very well-known book about mathematical biology. It's the Murray book. It's called the lambda omega system. So why? Yeah. So I choose some lambda omega function, but basically the lambda omega system, you can just you put it on the complex. You do x plus iy. You take the derivative and you obtain that, and you can compute exactly the solution. And asymptotically, you have this limit cycle, which is on the units circle. This is the asymptotic solution, and you can prove everything. Okay, and so we assume that we can do whatever you want. It's a toy, and we assume that the time is in milliseconds. And if the time is milliseconds, then you can slow down. You put a factor here, and you slow down the time by 3, and it roughly gives you 19. So let's say 20, and which gives you 50 hertz, right? Because for us, it will just be, for mathematics, it will just be a letter, F, but from neuroscience, the F is fixed. So let's talk about numbers here. Okay, then we add noise. And in essence, that's what we see a lot. In neuroscience paper, when they try to make some irregularity in low models, they just put a Brownian motion. This is a stochastic differential equation, and we had just a two-dimensional Gaussian noise, and that's what we observe. So at the left is the output of this model, and at the right is, there's two things. One thing is an output of conductances GE and GI in a network model. It is also a mathematical model, but much more complex. You cannot you cannot analyze it mathematically, or hardly. And this is a real output signal. So it's a voltage in of V1 in a monkey, a macaque. And so yeah, it's not bad. I mean, but so for example, this one, the first one. So here, mu x equals mu y. It's 0.2. Yeah, it's not enough irregular. If you look at this one, it doesn't look alike, those two ones, because the amplitude, for example, it's always almost the same. It never degenerates. For example, here it's degenerate. Here it's degenerate, but here no, it never degenerates. And so you can increase the noise. So when you increase the noise,
yep. Sorry, Bejam, can we ask short questions during the presentation? So you show these complex oscillations, and it's difficult to compare them like that just visually. So might be possible to consider this power spectrum of frequencies or something like that.
Sure. I will come to that. Sure.
Come to that. Okay.
Yeah,
good.
I will come to that. Yeah, that's a tool. That's a tool. Yeah. The next slide, you will see the power frequency. Yeah, I will come to that. All right. So then you increase the noise, and still this one never degenerates. It's better, but this is too white in the inside, meaning that this is you could characterize that numerically. It never reached the center, so those signals sometimes degenerate. And okay, so yeah, so for example, the last, so let's compare the other ones with the spectrum now. So those are the corresponding, I will define, this is the PSD, I will define it. Oh, no, it's defined here. So what we do, so what we do to the C, that's why I put it on the slide. I wanted to define it before. It's just the Fourier. So you compute the Fourier coefficients. So for all the frequencies, and then you make a window, a sliding window, and you make the mean. So this is the last line. All right. And yeah, for example, so this one is known to be too narrow to resemble a real frequency peak. All right. And then so this one is not bad. So this one, the second one, is not bad, but it doesn't degenerate. So you could, depending on what you want to represent, this actually is not bad. But you miss something. You miss the irregularity of the signals. It's still too much regular, and it never degenerates. And afterwards, I will see what's coming from this job is yeah, the Brownian is it doesn't see, it's not enough specific, so you start to lose the main frequency here. All right, so that's I'm not I'm just analyzing. I don't want to put this kind of modeling to the garbage. I just want to see that what is able to do and what it is not able to do. So the Brownian is very useful, and it's still useful, but it lacks some things. And along the talk, I will bring even more arguments to that. It depends what you want to do. All right. So here it's kind of, yeah, you start to miss the frequency. Yeah. So all right. So we can do something. One of the points is that you could tell me, so some people are familiar with that. It's called your system has no shear, meaning that, let's come back to that. Here, you know, the derivative is 1. So you don't act so much in the tangential, in the angular speed when you put your noise, because here it's always 1. This is not a proof, but from that you can deduce that, and numerically you see it. We should maybe work on the proof of that. But and so to do something with in this direction, we add some shear, meaning that we add here a specific term and with another parameter. So now you play with 2 parameters, this mu and this alpha. And now still asymptotically, the deterministic system is still going toward the same solution. It's just cosine sine. So it's just the simplest periodic solution, cos and sine. But now, when you perturb it with the noise, you act more on speed, and that gives better results. For example, this. Another way to perturb is just to play, because the 2 parameters on the first place, and so the first equation and the other equation. So you get a little better results, but still we want to show you another thing. So you could do more and try to obtain more characteristics of brain rhythms with this kind of very simple arguments. So periodic plus noise, and try to work. But our thing was to put another model aside and to see what the other model do. So yeah, so you could study some features and try to play with this limit cycles plus noise. There are some limitations. You could try to improve these models to get rid of these limitations. So next, what we are doing, I'm presenting another ODE, and then in this ODE, we will try to identify parameters that have a meaning, a mathematical meaning. And with these parameters, we can adjust some properties of the signal. So our model is more focused on this parameter acts on that. Okay. And also it comes from the study from networks. So it is a two-dimensional, but it comes from our play, our knowledge from the network stuff. So we will try. So let's read what's in this slide, the second line. So we will play with three parameters, and these parameters are related with the frequency. We want to play with the frequency, with the amplitude, and we want the signal to sometimes be able to degenerate. Okay, so as I said, really, this model came, that's the real historical path of this model. It started with this kind of network. So this is a link key integrate and fire model. It's a network. I just put one single equation. I just wanted to avoid some notations. But you have, for example, 500, 1000 ODE equations. And it's very simple. The C is a positive number. So the V goes to 0. If you do nothing, it goes to 0. But you add two terms. This VE is a positive number greater than 1. So if the GE is positive, this contribution makes the voltage climb up. While this one, the VI, is negative. So it makes the voltage go down. So this is an excitatory term, and this is an inhibitory term. So this is also a big thing in neuroscience, because local population of neurons, it's a known thing, and much things have to be studied in there, but it's known that the potential that we observe are linked to excitatory and inhibitory inputs. And here they are. Here it's my excitatory inputs. So here, just I will say it's not so clear when you try to read it. There is a more explicit formulation, but I just wanted to tell you that by speaking. So there's a drive, a stochastic drive, because if not, nothing happens. Let's say it's this one for D for drive, and then when the network starts when neurons start to spike, there are some coupling terms, some interactions between the neurons. And so this is going to make, this is the conductance here, right? And you have the same. So this is the excitatory conductance, and you have the same for the inhibitory conductance. This is the idea of these networks. So this is a very, very studied thing. Things are not so clear, but there's a lot of papers on that. And this is an example. It's an unpublished numerical simulations, and here you can see the GE and GI. And one big thing is that this is a big thing. This is a parenthesis, but this is a big thing. Is that it is also observed from the neuroscience measurements that, or studies, that the GE and GI are correlated. You can see that in the networks. They work together. So when the network is stimulated, if it is enough stimulated, the GE and GI work together. So for example, when you do the Brownian, this is not present. And also some people sometimes just don't consider these connections to be enough important, so they put some independent stimuli in GE and GI. So it depends actually, but the point that I want to make here is those are correlated.
Sorry, Benjamin, could I
Yes.
ask a question?
Yeah, sure.
Well, you told us that here are lots of these equations. So this is a network, and these three equations are for one neuron, yeah.
Yeah,
and
sorry.
estimation is through the neighbors, yes. So what is the summation sign here?
Yeah, sorry. So I apologize. These equations are not clear, but yeah, let me explain. So there are two summations. So first one, you have, for example, a stochastic process typically. So also I didn't make it so clear because it's a principle, right? So but the thing is, for example, the first term here, it comes from a stochastic drive. So you have a stochastic process, and then it's like a clock. And when a clock rings, this, for example, is a delta function, and you have a jump on GE of an amount of this coefficient SD1. This comes, it's a stochastic. It's not related to the neighbor, right? This one. Then this one is related with the neighbors. When one of the presynaptic neurons spikes, the neuron see it. When one of his presynaptic neurons spike, this one see it. So, and he sees here, it's the here it sees the yeah. So it's the E presynaptic neurons.
Okay. Yeah.
Okay, and then you have the same for the eye. Actually, there's a there's a mistake here. The usual notation is to put the Q, and the E is to change. So because here it's so this term is for the presynaptic excitatory neurons, and so the Q means either I or E, depending on the nature of the neuron, if it's excitatory or inhibitory. So I hope it's clear. So it's I can tell you more about that. It's a classical it's a classical principle used in some papers. And for example, yeah, there's a bunch of papers which use this principle. So stochastic drive, and this can represent any external event. So you could also put some specific, like orientation stimuli. You could add something there, or just some random events that occur in daily life or in other part of the brain. And then you have these connections which take place in the local network.
Okay, I see. Okay. Thank you.
Yeah, you're welcome. And then those are outputs of the network. So these are the GE. So for example, let's take this middle one. So you have the GE in purple and the GI in green. And the point here is that in the network they are correlated. Okay, then let's move on. Okay, so this comes from this is Scholarpedia. It's it's a good summary about what it's known. It's the excitatory inhibitory balance theory. Okay, so this is a mix between model and recordings, and you see they're correlated, right? In certain circumstances, they are very much correlated. And again, this comes from the model, and again you see a clear correlation. Okay. Okay, so let's move. I don't know how much time I have.
Well, usually we have our seminar 1 hour, so we start at 5 minutes later, so you have like about 20 minutes.
Yeah, that's good. All right. Okay, that's the model that I'm going to present now. So it doesn't come from nothing. You can see, so it's a cubic. So you could say, so it's real. It's inspired by Fitzhugh-Nagumo, but it's not, because you have the U and the V here, which are typical from prey predators model. So this model, really, that's the real story. It's inspired by, from one hand, it's Fitzhugh-Nagumo, and from other end, it's Leslie Gower, which is known in the prey predator model. So I will mention one other of collaborators, who is Aziz Alawi, who works with also Vitaly and Anne. And so he has a couple of papers on this model. So yeah, so this comes from Le Havre, this inspiration, to summarize. And okay, so now I will discuss the characteristics. But so really what's the motivation from this model is that we wanted to resemble a little bit the GE and GI time courses that are observed in networks of E and I neurons. So the Fitzhugh-Nagumo is not good for that. The dynamics doesn't look like, the Leslie Gower not so much, but putting the two together, yeah, this works. Okay, so A1, A2, B, C are fixed, and the K, epsilon, gamma will be allowed to vary. Okay, so you can prove this. Okay, if you start with U positive and V positive, it remains positive, which is good because the conductances are positive, not the voltages. And again, this comes from Leslie Gower because prey and predators are positive. So so you do have an absorbing set. This will actually, just for math, if you put reaction, if you put diffusions on there, this will also work for the attractor. I didn't prove that, but as I see it, I think it will work. Okay, so let's have a look. For example, so yeah, usually, so if U equals 0, then you stay there. So the whole line u equals 0 is a line of solutions. The same for v, mean of trajectories, right? And so I just consider the positive stationary points you have here 4. So you have 2 very close to 0, 0 because the parameter a2 is very small. All right, and okay, and then no, it's the C. Sorry, the C is very small. So the C is very small. So you have 2 stationary points here, 0, C and 0, 0. You cannot distinguish them on the biggest picture. And then you have this U star V star, which is important. And you have this other one, and this is the null clades, right? So basically, those are the null clades. Okay, so in this case, you have a limit cycle. But
sorry, Benjamin, but
yes.
it's too small. The arrows is too small. What points are stable? And
yeah, so you can see these 3 blue points here. You can see my
yeah, we see the cursor. Yeah.
Okay, 1, 2, 3.
Yeah.
You see, but here there are 2, but
yeah.
they are here, but it's very small here.
Yeah, but yeah.
Yeah, so here you have here it's a saddle.
Yeah.
Here's it's a saddle. Here also, so these 2 ones are saddles. This also, so you have 3 saddles, and this is, in this case, this is a source. It's repulsive. So U star V star, it's repulsive in this case. So for these values of the parameter.
Okay, so there is a stable limit cycle, right? So this a red circle is a stable limit cycle, right?
Yes, it is.
Okay, thanks.
Yeah. Yeah. There's a proof. So yeah. So you can prove easily the existence, the uniqueness. It's hard work. I didn't look the details. It's hard work to prove. There are some proofs of that. I did it in detail for the Fitzgerald stuff. This one I didn't, but there are some papers on that, so I believe them. I think this is true. It's unique. There's a unique limit cycle. Okay, and then so there's an interplay. Let's fix gamma. We fix the gamma. There's an interplay between epsilon and k, and it's the computations are quite simple, and you can prove you can derive the off bifurcation line between k and epsilon. The results of the computations are here, and so this gives you a line, you know, between epsilon and k. Once you have computed the stationary point u star, once you have computed u star, you have a line or a curve between epsilon and k, which gives you the bifurcation line. So here it is. So for fixed k, when you increase epsilon, you go from a limit cycle towards a sink. When you fix epsilon and you increase k, well, it depends. Usually you go from a sink to a limit cycle, but yeah, at this point you can have some other behavior. So here are 3 examples. You fix k and you so you fix k, you decrease epsilon, and you go from a sink to a limit cycle. Yeah, another thing, this is to illustrate that when epsilon is very small, so you have a limit cycle, and you can use the slow fast analysis. So it's a nice exercise, a nice example for slow fast analysis. For GE and GI representation, the epsilon very small, it's not so good. Okay, so we will the other are more used in the next discussions. Okay, now this is the effect of varying k. So basically, when you increase k, the amplitude of your limit cycle increases. So this is important, but because it gives you a practical way to increase the power, right? So it increases the power, it increases the amplitude of the signal. So in the range that we consider, the larger k, the larger the amplitude of the signal and the power of the signal. Yeah, so just, yeah, those are things that mathematics can bring. Okay, so as a conclusion for this brief study, you can change between a sink and a limit cycle. So this will be important for degenerating the signal. For the size, for the power of the signal, you can play with the k. And you can increase or decrease the frequency by a change of time. So meaning when epsilon gamma, when the product epsilon gamma is constant, the trajectories doesn't change. So keeping this epsilon gamma, I'm sorry, it's not registered, right? Or you are registering? No.
Yes, it is registered. Yes.
Okay, sorry for there's the phone.
No problem. No problem.
Okay, so let's continue. So if epsilon gamma is a constant, and you for example you increase gamma, you will increase the frequency. Or if you decrease epsilon, right? So you have a line to increase the frequency. So let's summarize it. You can play now on the amplitude, the frequency, and the degeneracy of the signal. And so the next step is to put some irregularities. So we put some stochastics. And so the way we do it is that we generate uniformly distributed variables. They take values between -1 and 1, but we and we iterate, we update the values k, epsilon, gamma with this algorithm. Where we are going to act is on the range. We allow only a certain range. So I didn't put here, it's kind of border conditions. When we reach the border, we don't allow the parameters to escape some range. And this will allow us to fit some biological outputs. And so just 3 slides, we choose 3 results from real observations, from measurements. And we confront this model about, is this model able to reproduce that? Okay, this is a preliminary thing, is that there's a known thing. So usually this comes from Narison. They say, well, the GI is 3 to 4 times the GE. And with it's an output of the model, and I think the dashed line is 3.5. So there's a very closed relationship between the U and the V, right? And you can see it. You can see it in this network model. This one, which is a real observation, is just to so it's just my eyes. There's no for the moment there's no PSD, but it looks alike, right? So, and what we like in this signal, it's you have the rhythm, but then it stops, then it comes back, then it stops, then you have this clear rhythm here, then it stops, and yeah, neuroscience guys like it in general. Okay, now we confront it with some outputs. So this is a paper for Xing and all. They make measurements on awake
Sorry,
kids.
wait a minute. Do I understand correctly that in previous slide you changed 3 parameters k, gamma, and epsilon periodically? Yeah.
Not periodically,
No?
randomly.
Right. Randomly. So they changed randomly with by the change of u. So you had u with I, yes, u big, which was distributed in the from -1 to 1, and this
Yeah. So the
was
so let's bring it. The capital U, it has nothing to do with the lowercase u. So the capital U is the random variable, which takes values uniformly between -1 and 1. So at each time step, so 0.1 milliseconds, we choose a different value of U1, U2, and U3, and we update K, epsilon, and gamma according with this formula.
And these 3 U's are different, yeah?
Yes, they are.
So every time step you update these 3 K, epsilon, and gamma randomly, but you update them for the by changing a little bit, yes, because this you have yes.
Yeah, you have these coefficients in the front, so basically it's
So there is some drift maybe, yeah. So they change slightly. Okay, I see.
No, sorry. I think that there's some probably misunderstanding. It's a random variable, but not a random walk, right? It's not that it changes step by step. Alexei, what you say when you say they change slightly, you mean that they do some small jumps, right?
No, yeah, that's right.
No, but it's not what is written here, because Benjamin, you write it independent variables uniformly distributed. It's not a random walk what you write here. It's just random jumps. It can jump in any place with equal probability. So you see the difference?
But so
the weights are very small. So if epsilon,
So we start for let's focus on epsilon. So epsilon, I mixed up the two notations. I will write epsilon I plus 1 if you want, but so the iteration. So you start with a value epsilon, and then at the next step, epsilon will take a value between epsilon plus 0.001 and epsilon minus 0.001. If it doesn't escape to a certain range.
Okay, I see. Yeah.
We constrain them to a certain range, and that's how we can obtain results.
So epsilon, for example, can really change like slowly, but by small jumps, going one way, another way, right? It
Yes.
in a random way, but not jumping randomly in the whole range of the values of epsilon.
Yes. No, it cannot do that.
Yeah. Okay, I see.
Okay. So in the left, this is measurement paper. I think it's so the reference is here. My guess is Journal of Neuroscience, but we could check that. So you have awake monkeys and anesthetized monkeys, and you see. So this is basically the Fourier coefficients, and you look at it across the time. Okay. So this is the spectrogram, right? So when he is awake, you see a clear bump here around 60 hertz. So forget about there's a line is to forget about the initial time, and on the right it's more at 40, and the power is less. So that's a thing that we can do. And here, basically the C is the mean of A across time, and the D is the average of B across time, right? And so at the right, so constraining, so what we do, it's the model, but constraining epsilon, gamma, and K to certain ranges, yeah, we can reproduce that. So both the frequencies, so you see the frequencies here, it's more than 60, it's more 70, 65. Yeah, so it's rough. We don't want to be exact, but we get this range here. So it corresponds to awake, and here you are more at 50. Here it's 40, but okay. And also the power is 0.6 here, and here we have 0.5, and here it's 1, and here we have 1.5. But just to say that the parameters, it's you can put that on this direction, and it's random. Maybe we could choose more directed paths. Okay. And here, the D on the right is the spectrogram. So you have kind of a similar behavior. All right. So there are 3 examples. This is the Jaya paper. Jaya paper. So there is a correspondence. So when the contrast increases, so this is a kind of logarithmic scale, but when you increase the contrast, you have changes both in frequency and in power. So for example, here at the peak of power, it corresponds to like 40, a frequency of 40.
So they show this picture to monkeys, yes?
Yeah, exactly. They show this picture to monkeys, and they record it with LFP.
Mm-hmm.
And then, yeah, they measure the frequencies. And so, yeah, that's what we did here. For example, at 40 hertz, you have here a max. So this is normalized, right? And then we could also choose like 25 frequency and have a power which is around 0.2, 0.3. So here you have like 0.2, and here also, right? So here, for example, so no, 30, like let's say 30 here corresponds to 0.25, and here, yeah, it's yeah. So it's an idea, right? So you can do that with the models, playing with the basically to go from the blue to the purple. You have to decrease k and also to increase epsilon, but then maybe you need to adjust because you're also playing with the dynamics, but it works. And the last thing is something related to you repeat some stimuli, and you can observe. So forget about the left one here, but just the peak, the bump on the gamma frequency, the frequency increases, right? So yeah, this is also something that we can do by basically we increase k, and then you need to adjust epsilon and gamma, right? So basically, what comes from that is that you need some. It's like when you do the periodic plus noise. It's a little bit too raw. So if you choose some parameters, you can be more specific. And furthermore, this model that we considered has the property to quite accurately to represent GE and GI. So then from this, what's the use? Why is it useful? For example, this is just an example. It is known that the GE in GI in some networks it's like a mirror. It really represents the activity of the network. So from the activity of GE and GI, represented by that, you could represent a network scenario. So it could be useful if you want to lower the dimension of your network. You can use some tools like that to try to simulate the activity of a network by looking at some representation, some projection of the network. This could be a projection of a network. All right. So just one or two slides just to say that yeah, something is messed up here. I'm sorry. Okay, let's just correct that. Just want to show that. So I think this one goes there, and I just need to drop that, and I then. But I think it will stay. So it's not the entire screen. You see the entire screen? No.
No,
we don't see the screen. No, we see we see you. But okay. you can write on the blackboard. We see the blackboard.
No, let me. I know how to do that. I did it with Anastasia, so I should be good at it. I just remember it's where it is.
What you are looking for? How to share screen or what?
Yeah. I got it.
On the top of your screen is a white square written share.
Okay. Yeah. Oops. Screen share. Okay, got it. Sorry, I'm good. Few seconds. You should see it. Oh no, just to say. So when epsilon is small, so the slow fast theory applies. And here, so some things are well known. You know, you follow some manifold. So it's an attractive manifold. You follow it from G to A. So this is well known. Then you jump. This is well known. Then you follow the attractive manifold. But then the C is not so clear. What is the value of C? Because you see the derivative here becomes positive after the green line, but still you stick to this manifold and it's repulsive. So this is called the canard. And then you jump from C to D, right? So this is all very well known and very intuitive, but the C is not so clear. This is really a mathematical interesting stuff. What is the value of C? And by some technical computations and techniques, you can relate how you pick up a line when you cross, for example, let's say you pick up point 1, at which x coordinate you cross the y coordinate point 1, you write it at x0 equals k epsilon plus O of epsilon, and then you can compute the output, the y coordinate of C. So there's a close relationship between the coordinate you enter your attractive manifold and your coordinate you exit your coordinate manifold. So it's called an entry-exit problem. And there were some other papers on that, a few ones that I didn't know about, and but yeah, that's a very interesting application of those computation. And so we made an original contribution to that in 2 papers. And this is a nice mathematical exercise. Well, that's it. Thank you.
Well, thank you very much, Benjamin, for this interesting presentation. I see there are questions, and I think it's Mali Banerjee from India who is visiting us, also good friend and colleague. So please, Mali, go ahead with the question.
Yeah, Benjamin, thank you very much for very nice and illuminating talk. I was just wondering about one thing, and this question I discussed with a couple of people, that when you are introducing noise into the system, mainly for the periodic situation, you have introduced some sort of additive noise. Of course, you can keep your mu values under control such that positivity of the solution is ensured. But have you thought about considering sine winner kind of bounded noise? That is a new theory coming up that is called bounded noise. You can, for example, towards the end of your talk, you considered uniformly distributed random number between -1 to +1, and they are jumping from one level to other level in an uncorrelated way. But if you have appropriate correlation among 2 steps where it is jumping from previous time step to next time step, so I think that kind of bounded noise will be much more interesting to explore, such that depending upon the correlation of the noise steps between 2 consecutive time points can give you some better result. And if you wish, I can send you some paper in that direction and some literature also.
Yeah, thank you. We'll be happy. Yeah, I don't know this new theory. I will be happy to have a look at it.
Yeah, just for example, simply we can say xi t is a white noise. If you consider sign of xi t, it is always lying between -1 and +1. It is a rough description, but there are some appropriate governing Langevin equation whose solutions are appropriately bounded noise. And just out of my curiosity, I just wanted to know, because recently I worked a little bit in one case with Vitali also, that is slow fast time scale model in presence of diffusion also. So in the context of neuronal brain dynamics, that birhythmicity model or system having mixed mode oscillation, that have some prospect in that area?
Oh, for sure. Because you have the Hopf bifurcation, there is this thing going on. We didn't look at it in this paper, but for sure, when you go between degenerate and limit cycle, you see that. That's what was one of our points, is to introduce degenerescence. But this corresponds to an off bifurcation, and near this off bifurcation, there are mixed oscillations.
Yeah, for example, on the Hopf bifurcation curve, if you have a Boutin bifurcation point, so there will be two limit cycle. One is unstable, that is surrounded by a stable limit cycle, and noise actually can break this unstable barrier such that you can have a stochastic resonance between these two structures, and I think that have some applicability in the neuroscience.
Yeah, that's an interesting question. We are also let me mention, do you know, it's recorded, I don't care personally. You know Ranjit Upadhyay?
Yeah,
you know him? Yeah. Yeah, we have a work with him. Yeah, so he started with some of his young colleagues, he started some study about that, and we have a collaboration with him where we discuss this question. It's deterministic, it's not stochastic, but yeah, for sure, I'm very interested in this kind of things from a mathematical point of view.
Okay. Thank you.
Okay, thanks. Other questions, maybe? Bенджамин, you mentioned when you introduced your model, you mentioned that it's not so good for Hitsu-Naguma. Could you repeat and explain why this approach is, you don't apply it directly to Hitsu-Naguma, or maybe to Hodgkin-Huxley? Why do you invent this special model?
Yeah, so it's the time courses. I should prepare this answer. It's a really, we studied that carefully. The dynamics in the Fitsug-Nagumo doesn't look like the conductances, meaning that the GE and GI start together and they increase together. That's not the case in the Fitsug-Nagumo.
They are in some sense in opposite phase, right?
So, but let me bring you, so I will share again. So sharing is there. I will share with you window. Okay, you can see just, but it doesn't matter.
Yeah.
You see, for example, here, you see my set, right?
Yes.
So they increase together.
Yeah.
Fitsug-Nagumo is not like that. So you see,
Fitsug-Nagumo, they are more opposite phase, or what? Or
exactly.
It's not opposite.
Yeah, exactly. Yeah, exactly. Yeah. We can.
Okay.
We could take 10 minutes and put the things of Fitsug-Nagumo and compare it, and this model is much more close to that.
Okay, but if you take this model in the spatial case, so what it gives, even without stochastic coefficients, just deterministic.
Yeah, I don't know. It's an interesting question.
With the space variable, you did not write. No.
Yeah. So, but we have so which is interesting. We have the properties of Fitsug-Nagumo, meaning excite.
Yeah, I understand that. Yes, but
the oscillatory and yeah, I don't know. Yeah, really, we have to have a deeper look at it.
Yeah, but it can be interesting to see how it behaves in the space, in the spatial case, and even in two-dimensional space, not only one-dimensional but two-dimensional.
Yeah, that's right. Yeah. We have to look first at the dynamics. I look at it, but now that you answered the question from the excitability, the focus was to reproduce the GE and GI time courses. That's what the focus, and not so much the excitability. And so yeah, it will be good to focus on that question too.
Yeah, my last question. Could you return to, it's one of the last slides where you give examples of applications, and one application for contrast and another application for repetitions.
Yes.
Yeah, this one. So I don't, I cannot think about this contrast, but about repetition, it makes me think about some memory. So why, in fact, our brain reacts more after some repetitions? Because there is a memory, right? Effect.
Yep.
Why wouldn't you put some memory effect? Because you, in your examples, these three curves are independent. I mean, just the parameters are not related. You just choose this parameter.
Yeah, they are related because, but it's not formalized because we go from one to the other. There's a path, but
it's a path. No, but it's a random path. I mean, there is
no, it's not a random. This one, these three curves, I choose it specifically, and practically, that's a path, a chosen path. But it's meaning that. Let me correct that. I can. How do I realize these outputs? I have to choose some bounded intervals. For k, for gamma, for epsilon, I have to choose them. After the signal is a dynamical system with stochastic, but these three choices of bounded ranges, of bounded intervals, are related. So I think the question, but I didn't formalize that, and that's the question: are the repetition transcripts to the choice of this? I did not do that.
Yeah. So what I'm trying to say is that if you introduce some memory in your model, meaning that the values of k, they're not just random, but they keep memory about previous events.
Yeah.
And
so
then,
here they keep it's a one single memory, but yeah, we can keep more memory because the value of k I times plus 1 depends on the value of k I times so I times t plus 1 depends on the value of k I times t.
Yeah, no, but I mean, in these three curves, blue, green, and brown. Well, okay. Anyway, so
I understand.
Yeah. Okay. Yeah. Okay. Good. Thanks. Other questions?
Vitaly, just a moment.
Yes,
so here you are interested to interpret memory as in terms of delay or in terms of fractional differential equation?
No, certainly not fractional, certainly not fractional differential equations. You know that I'm really
actually studied this Fitzhugh-Nagumo model with fractional derivative just to take care of the memory effect in terms of Caputo sense.
No, really speaking, well, we discussed about these fractional derivatives. I don't know any justification of these fractional time derivatives in real applications. I don't know about that. No, what I mean memory, it can be either delay or maybe some other kind of memory. I don't know. I cannot specify it because I mean. I don't know how it works in reality, but maybe Benjamin can think about that.
Well, that's interesting because in the brain works like that. That's interesting.
Yeah.
Yeah, I didn't think about memory. In this.
Okay.
Yeah.
Right. Okay. Good. So we have something to think for the next time. Right. If there are no other questions, then thank you again, Benjamin. It was very interesting, very, I think, instructive for our listeners. Thanks again to everybody, and we will meet again next week or in 2 weeks for the next seminar. Thanks, and bye for now.
Thank you. Bye-bye.
Thank you.
Thank you very much. Goodbye.
Bye-bye.